name's Rachel. I work at Galaxy. I lead the tech for our Bitcoin mines. And today I'm going to talk to you about what it takes to build an industrial Bitcoin mine in 40 minutes. So there's a lot to go over. There's a lot of different components. I'm going to start with where I started, and then I'm going to go over the key components of a large-scale mine, and then I'm going to explain how these components communicate, and then we're going to build the network out together. So before we get into that, I just want to bring everyone's attention to what miners really care about. So we are always thinking about maximizing revenue, and we do that by maximizing uptime and by minimizing our costs. So it's really important to have a very efficient operation because power is so expensive and it's such a competitive industry that any way you can have an edge, you want to take it. All right, so this is where I started. I started learning about Bitcoin mining just in my apartment. I had a couple S9s that were given to me by different people, and I started doing some packet sniffing and learning about the Stratum v1 protocol and what was really going on underneath the hood. And then, oh yeah, there's the video. Yay. And then I was working on the Stratum v2 protocol, which is the next generation mining protocol, all last year. But at the beginning of this year, Galaxy acquired a very large mine in Texas, and so that became my full-time focus. And this is like a short video of the mine. So it's like 4 football fields long. It's giant. That's the fluid mechanical system being built. That's the substation that takes in power. That's the inside of the mine. All the miners are immersion dunked, so the immersion oil cools the miners instead of traditional airflow. There's the cooling system again in the substation. And then you can see kind of in the distance, well, I can't go back, but in the distance you can see a lot of wind turbines. There's a lot of wind energy out there. This is, that was the immersion mine, and then on this side is air-cooled miners, and on the other side is immersion. So you can hear how loud that is. If you have a giant mine of all air-cooled machines, it's really annoying. And then on the other side, this is immersion. So you can hear it's really quiet and soothing, very zen. It's really nice. So you just have this giant warehouse of these immersed miners. So let's talk about the key components. So obviously we have our Bitcoin ASICs that mine the Bitcoins. And then we have power distribution units, so PDUs, to supply power from our substation to the miners. We have a cooling system that removes heat from the miners. We have a really good server and databases, so we have a lot of custom code that needs to execute in a very efficient manner, and we have a ton of data we need to collect, so those are very important. And then we have our network devices that connect everything together. This is a picture of the fluid mechanical system. So immersion mining, it's really great because it cools the miners very efficiently, but it definitely takes a lot more setup to do immersion mining, and the cooling system is much more complex. Also, mines are typically really dirty. They don't need to be a tier 4 data center. You don't want to over-engineer and overspend money on a really nice data center when you could just be buying more miners. But with immersion mining, you have to make sure the machines are clean before you dunk them. So we have an ultrasonic cleaner to clean them. If you don't do that, it'll break the fluid mechanical system. All right, so PDUs, very important. Here's a picture of some smart PDUs. So there's 2 kinds. The top should say dumb PDUs, not smart PDUs. So dumb PDUs, they're just really basic. You plug them in, you plug in your devices, you get power. You can't query the device for any information at all. And then smart PDUs, you can ping them programmatically and get a lot of real-time data, real-time insights into how they're performing, how much power they're pulling, And it makes it easy to identify, if one is down, and then we need to troubleshoot immediately, because if we can't tell that something's down, then that's minor uptime reduced, and that's a reduction in our revenue. Then we have network switches. So network switches connect all these devices together. We have unmanaged and managed network switches. It's similar to dumb and smart PDUs. So unmanaged, you just plug in a switch. It connects the device to another device. You can't ping it for information, but it gets the job done. And then managed switches, you can programmatically interact with them. You can see what devices they're connected to. You can see like the health of the switch. And again, that helps the troubleshooting team more easily identify what's going wrong faster so we can troubleshoot. All right, so this is kind of a dense slide, but the servers are really important. So you have like a lot of custom code running a lot of different protocols, which we'll get into, and they all need to execute at the right time on the right systems, or again, you risk major downtime. So you definitely want high performance servers. You want a centralized VM management system so you can have separations of concerns. You want to have different VMs for your site code. You want to have different VMs for your DNS DHCP server. You want those things segregated just in case there is a security breach, like not the entire system is compromised. So for data management, again, we get a ton of data on the site. And we want to have on-prem data because a vast majority of the systems, they are still on if we lose internet. And you're in the middle of nowhere, Texas, so internet goes out a lot. Like the weather is really harsh, like very extreme highs, very extreme lows, and it impacts a lot of the supporting system. And so if you don't have on-prem servers and databases and your internet goes out, like you just have a dark period. You have no way to collect data, but even worse, you have no way to monitor the site. Like the people on site have no idea what's going on. Maybe like the cooling system's messing up or a tank is overflowing, but there's no way to find it unless someone walks by it and sees it. VMs are also really good because you can host a Stratum proxy anywhere, but we have VMs just to host Stratum proxies to aggregate connections, and that reduces latency and increases communication between the miners and the pools, and that is an efficiency gain that maximizes revenue. So back to on-prem. Again, it's really critical that we have access to on-prem data, but at the same time, like even if you have the best storage setup, eventually you're going to run out of room. So you still need to have cloud databases and backups. I realized that like data replication between two databases is pretty straightforward. Like a lot of database tools have that automatically built in. But if you want to only replicate some of the data, that gets a little trickier. So definitely something I didn't realize at the beginning of the year was how hard it would be to manage both on-prem and cloud services. So the message queue has really become a good friend. I was starting to look into like how to manage these databases and realize that instead of just like having logic in the code to write to like multiple databases, we can get really messy. You could replace that and send it to a message queue system, and that message queue system can send it to the on-prem and the cloud if the internet is up. Messaging queues are also really good to trigger events and workflows. So in like a live engineering site, nothing is isolated. Everything's really interconnected. And if like the PLC on the mechanical system goes down, then that needs to trigger another code that sends an alert and needs to trigger another code to like update another piece of data so the troubleshooting team can see what's going on. So messaging queues really help with all of the above. All right, so now how do we get all of these systems to work together? We need them all. They all speak like a different language. So I'm going to talk about the common protocols you'll see at mine. First is the Modbus protocol. It's designed to facilitate communication between various devices in a supervisory control and data acquisition system. So that's SCADA. And it's really ubiquitous across many industries. PLCs use them, and it's a very useful protocol. SNMP, Simple Network Management Protocol. So I use this all the time. Basically, you can like push and pull information, so you can ping like your PDUs, your switches for information, but you can also execute commands. It's really good for alerting systems and at the end of the day, maximizing uptime. So SNMP and Bitcoin. Again, for the switches, and then for miner location tracking. So the switches is what connects all the devices together. And if you have a giant mine and you need to find one miner, it's like finding a needle in a haystack. So if you don't have like really robust code to interact with your network switches over this protocol, your troubleshooting team is not going to be able to find anything, and everyone's going to get mad, and it's going to be a giant mess. And then for PDU metrics, like you need to have that PDU data so you can reconcile your power bills, and also for your hosting clients if you host. Mining protocols. So Stratum v1 and Stratum v2. Stratum v1 has been around for like a decade. Most of the pools and firmware you see are all Stratum v1. There's a lot of inefficiencies with Stratum v1. It's really bandwidth intensive. And Stratum v2 came about to improve that. So it's the next generation mining protocol. It addresses a lot of the efficiencies in Stratum v1, including replacing the JSON RPC packets with binary, which is great for miner bandwidth. It's currently in active development and not really supported by any stable firmware. But the Stratum Reference Implementation Team, SRI, they're amazing devs, and if you want to join that project, it would be really helpful for the mining ecosystem. So this is what Stratum v1 looks like. Like I mentioned, it's JSON RPC. So the miner subscribes to a pool, the pool says okay, and then it sends a block template for the miner to start mining. And then the miner finds a block that meets the pool difficulty and sends it back. And you can also notice in the second message, the miner sends the pool its worker name and password in plain text. So this is an area that gets attacked a lot. So the connections look like this. If you don't run a Stratum proxy, that means that every single miner has one connection to the pool. If you have tens of thousands of miners, that's a lot of connection. It's very, very bandwidth heavy. It's very hard on the network. So Stratum v2 benefits, again, it uses binary packets, really reduces bandwidth and helps the switches out. It enhances security. There's no more plain text miner worker name and password to the pool. It's got an encrypted handshake, so that prevents man-in-the-middle attacks. And it also gives the miners the option to build their own block template. So if they build their own block template, they get to select their own transactions, and they also get to vote on BIPs, and they instead of having the pools vote, so it gives the miners their voice back. Okay, so we went over the protocols, so now let's talk about the firmware that the ASICs run. So the firmware is what runs the Stratum protocol, and the first one was CG Miner. It's like 10 years old now, it's open source, it's archived on GitHub, and it's basically the basis for all mining firmware. So a lot of companies went in, forked that repo, and turned that into their stock firmware and their third-party firmware. Stock is firmware that just comes pre-installed on the ASIC by the manufacturer. And there's really not that many third-party options. And again, like a lot of them are just clones of CG Miner. And there are some new implementations that are written from scratch, but CG Miner is so ubiquitous that these new implementations actually support a lot of the CG Miner commands. So there's no docs in mining. It's really hard to figure out how the firmware works, how the APIs work. I'm really fortunate to work with a couple amazing devs, Spencer and Jazz, and Spencer was working on some of our mining firmware interface code, and he sent me a Slack message, asked me if I had any firmware docs, said he'd been like searching for a very long time, and I was like, absolutely not, there's no such thing. Like, you basically just have to get into the mining dashboard and like reverse engineer some of the HTTP requests, or you have to do packet sniffing to see what's going on. So interacting with the miner dashboard. Miner firmware comes with a web GUI. It's very basic. It's like straight out of the 90s. It's got limited controls. You know, you can change your pool endpoints. You can reboot a miner, simple stuff like that. Like you can view real-time stats. But if you really want to get like the full picture of the miner, if you want to fine-tune the overclock settings, things like that, if you want to store any of the data, which you do want to store the data, then you need to interact with it programmatically, and a lot of times that's via HTTP or netcat commands. Okay, so quick recap. We have key devices at the Bitcoin mine, miners, PDU, cooling system, network switches and servers. We've seen the underlying protocols and how they all integrate together. So now let's look at the network. I'm not a network engineer, I'm a software engineer. When I started this, I did not realize like how important a really good network is to a Bitcoin mine. Like you cannot function without a really good network. So the way that I like to understand things is starting really simple. So I'm gonna start with where I started, with one miner in my apartment. So we have the pool on the external network, and then internal to our network, we have our modem, which connects us to the outside world. We have our router, which is connected to the modem with one of the Ethernet ports on the router. And then we have our miner, which is also connected to the router with an Ethernet port. And then a little power outlet to power the miner. And then we have our laptop and our database to collect our miner stat. Let's go back one. So if you saw the miner IP address in the last slide, it was a 192.168 IP address, and that IP address was automatically assigned to us from our router. That's done through the DHCP protocol, so it assigns IP addresses to network devices so they can communicate. So the router assigns an IP address to devices connected to the network switch. Like the router has a built-in DHCP server which handles that. It maintains a table of the IP addresses and the device MAC address. So like your miner MAC address is going to be the tie for the router to know what IP to assign it once we do static assignment. And then now devices on this network can all communicate. So we have the basic router with 4 Ethernet ports, 1 to the modem, 1 to the miner, 2 free. And then now we can connect 2 more miners. So now we have 3 miners, still dynamically assigned an IP address. But in our code, we have hard-coded the last IP address from the first miner, and we're not pinging the other 2 miners. So we need to expand our code and tell it to ping those other 2 miner subnet or miner IPs in order to collect that data. So what happens if we need to unplug a miner? Like there's something going wrong, we need to refresh it, so we just unplug it, plug it back in. And now we get a different IP address, but we've hard-coded our last IP addresses. So this is a problem now because I think I'm collecting data for all 3 miners, but I'm really collecting data for 1. So what we're gonna do in this stage is we're just gonna statically assign an IP address. We're just gonna say, okay, call these miners 10.0.0.1.2.3. I can hard code that in my code, and I can unplug my miner and plug it back in. And because the IP address is tied to the miner's MAC, it will still be persistent. So there's problems here. One I've been glossing over is the power. There's like no way my apartment could actually support 3 of these miners. And also, let's see, we want to add more miners, and we're out of ports on the router. So what do? We add a switch. And we're going to add an unmanaged dumb switch right now. So we have a 16-port unmanaged switch, which means we can expand to 16 miners. And again, I'm glossing over power. The router then had 2 free Ethernets, so we might as well add 2 more ports in. And now we have 48 miners. Again, power is a big concern, and also we look at our pool dashboard, we're really excited, like we've got a bunch of miners now, and our revenue is not as high as we thought it would be. And so I go into my router and I'm like, okay, like what's going on? And I see like the router is at capacity. There's a lot of packet drop errors happening. And I'm realizing that like my network cannot handle this amount of traffic, and my shares to the pool are getting dropped. So I'm unable to properly take full use of all my miners. Also, you know, someone's realized we're mining, and they've started DDoSing us. So that's like killing our network. We don't know how to like fix that. And we realize that we're getting man-in-the-middle attacked as well. Like we open up our packet sniffer and we like see some pool worker names and users that we don't recognize, and we're getting our revenue just siphoned off. So it's a lot of issues here. But yeah, that's the summary. But now it's time to move to our data center. Very exciting. So the initial data center setup, we've removed the modem and our basic router. We now have an ISP box. We've upgraded our internet plan. We've got a lot of bandwidth. Everything's great. We have a firewall now that'll protect us from getting DDoSed, amongst other things. We add in a core switch, and that's also going to handle like our routing tables. And then from our core switch, we're going to plug in our 16-port switches, but this time we're going to make them managed so we can actually ping them for information. So the last thing, and then we have a server. We've got a really nice server now, not a laptop. And then we have a local on-prem DB, which is fantastic. So let's deal with power. So now we need to start using PDUs. We're using smart PDUs here, so we can collect a bunch of really good data. But we need to connect these PDUs to the network. So they're going to take up 1 port on our switch. So now we actually have 45 miners, which is very sad. And as a miner, like I'm really not in the business of downsizing, right? Like I never want to have less miners. So let's add another switch, and let's get us to 60 miners and 4 PDUs. So this network is very flat. There's no sort of segmentation between the PDUs, between the miners, between groups of miners. Miners are very chatty with that Stratum protocol, so there's like just a ton of traffic, and uptime is beginning to suffer. So there's a couple things we want to do. We want to start using VLANs to segment our network, and then we also want to completely redesign our entire network architecture. So with VLANs, it's a virtual local area network, and it's just a way to create logical networks within a single physical infrastructure. They keep traffic separate between different concerns, and they are a lot more flexible and will make miner location tracking a lot easier. So again, they provide network segregation, security as well, because now we have subnets in our network, so if something goes wrong on one subnet, it doesn't affect any of the other ones. It improves performance because it reduces network congestion and latency, and it's also a much more flexible design, so we can scale up better. This is like similar, so just isolating traffic, improving security, simplifying management, and enabling expansion. When we are talking about subnetting and assigning these IPs, I think it makes a lot of sense to use different subnets for PDUs and miners and then management interfaces systems. Like, there's a lot of ways to skin this cat, so there's really no right answer, but logically that makes sense to me. We always want to identify like exact PDUs because we want to know like how much that specific PDU was pulling over the course of the month. If we can't pinpoint which PDU is pulling what power, we have no way to like reconcile our power bill or bill our hosting clients. So we choose static IPs for the PDUs, similar for the switches, and of course we use VLANs to segregate miners into groups so they're easily identifiable. All right, so upgrading our network architecture. We're gonna go to a 3-tier system. This is like a pretty old system, but it's been used for a while. It was introduced by Cisco. We have a core switch on the very top that connects to our firewall, that connects to our ISP box. And this core switch then goes down to the distribution layer. So at this layer, we've got another set of smart switches, and they are all connected to a set of access layer switches. So it's just like a little tree, and the access switches connected to a different distribution switch, they can't really pass traffic directly. They have to do a couple hops. Okay, so just going in a little bit deeper, the core layer is a high capacity, high throughput switch that can handle the aggregate traffic from the distribution layer switches. The distribution layer controls traffic flows, enforces policies, and performs routing between the VLANs and the subnets. And then these switches act as intermediaries between the core switches and the access layer switches and enforce policy and segment traffic into different subnets. The access layer, finally, connects the end devices, miners, and PDUs, and control access to the rest of the network. So some benefits here is that we get improved security because we have segmentation which isolates our critical components. We've got better performance. This optimizes how traffic moves through our network. And we have increased scalability. You know, we can add on more distribution switches and expand the network. So with one core switch, 4 distribution switches, and I forget how many access switches, we can get 1,152 miners in this setup. So let's expand. Let's add another core switch. We'll add another set of distribution switches and access switches. So we've got 8 distribution switches and a bunch of access switches, and we can get this up to about 35,000 miners. I think there might need to be some more distribution switches, but you get the point. You just keep scaling this more and more, and you can add more and more miners. So there are some problems with that previous design. At a certain point, like your core switches might start to get overloaded, and then you suffer like similar things that we saw with our other network designs, like our SNMP walks aren't working anymore, like they're dropping packets. Maybe the SNMP walks still work for the PDUs because we're only asking for like one data point. We're only asking like, hey, what's your power draw right now? But for the switch, we're asking it like, what are all the devices that you're connected to? And that's like a huge packet to pass back. So the 3-tier network is no longer good enough for us. We're not able to do miner location tracking. Everyone's very mad at us, and it's just a sad day. So we move on to the spine and leaf architecture. This is a newer model. Traffic moves from east to west in this architecture, as opposed to the 3-tier, which moves north to south. So like the 3-tier, you know, you move up and down between like the core, the access, or the core, the distribution, the access. And with the spine and leaf, all of the spines are interconnected with each other. So you have like this routing layer, and the next layer is the spine. That's pretty analogous to the distribution layer, but all the spines are connected to each other. And then underneath that, you have all of these leaf switches. And all the leaf switches are only like one hop away from each other. So everything is a lot better here. And we can, if we scale this out, we can get like 46,000 miners on a design like this. So some design principles for the spine and leaf. Again, the spine switches are interconnected to all the leaf switches. The leaf switches connect to all the spine switches. They don't connect to each other, and again, they're similar to the access switch. And this is like a non-blocking architecture. So any device on the leaf can communicate with any device on another leaf in the same number of hops, which is very cool. Looking at kind of the differences between the spine and leaf and the 3-tier, so obviously the topology is different. We talked about how the traffic travels differently through each model. Spine and leaf has predictable pathing. So spine and leaf has only one path between the leaves, so latency is predictable, where 3-tier has multiple paths, and that leads to variable latency. And then the spine and leaf is a lot more scalable than the 3-tier. You can keep kind of expanding. You don't hit that core switch issue. The topology here, it's a lot flatter of a structure, and it's a much better modern solution for a Bitcoin mine. So just a recap of all the network stuff, it was kind of a lot. So we had the spine switches. They're the high bandwidth, high performance switches that form the core of the network. All the leaf switches are connected to all the spine switches in a full mesh topology, which gives us redundancy and eliminates a lot of bottlenecks. And then we have the leaf switches, and those are connected to the spines, and they provide access to our miners and our PDUs. And then we still have the firewalls and the routers in the system, and of course, our precious management servers. So in conclusion, we covered a lot of different topics. Here's the highlights. So orchestrating a lot of devices is hard. I really feel like operating a Bitcoin mine is not really a Bitcoin problem. It's like an Internet of Things problem. You just have tens of thousands of devices that you need to make sure are working all at the same time. You need to make sure you have alerts, monitoring, data collection, a whole bunch. And then it's very important to have a hybrid on-prem and cloud solution. You're going to lose internet all the time. Even if you have backup internet providers, it's going to happen. You don't want to go into a dark period where you don't know how much power you're drawing. Our miner's still hashing, but we're not sending any shares to the pool, so we're just burning hashes for no reason, things like that. The network architecture is very important in order to scale and also for security. And then it's always important to be forward-looking in mining because the industry is rapidly changing, and you want to make sure you're able to adapt with those changes so you can stay competitive. Thank you.